Okay, so the goal of this video is to take some of the stuff that we've already done with transformations, and we're going to expand on it now, and we're going to talk about how do you apply the idea of transformations to individual points. So before, when we talked about transformations, we did it in a very broad way. We discussed how do you or what do the values a, b, c, and d do to a function? Where do they move them to? So now we're going to actually be very specific, and we're going to take the parent functions, and we're going to be able to exactly graph what the new function will look like using transformations on individual points, and saying, okay, some points started off at randomly maybe like 1, 3, and because of all of these transformations, now it's somewhere else, and we're going to be able to figure out what that somewhere else is. So before we do that, we're going to do some review about what we talked about already, and we're going to expand on those ideas a little bit. Okay, so what we already know is that if we have some parent function, which we call that parent function f of x, okay, we can call it whatever we want, there are 4 possible transformations, or 4 possible values that can transform the function using slides, reflections, and stretches on the parent function's graph. So I have those 4 set up here, and again, we've talked about this. There's an a value that's being multiplied on the outside of the function, a b value that's being multiplied on the inside of the function, we have a c value that's being added or subtracted inside of the function, and a d value which is being added outside. So we can have any of those show up. They might not all show up, okay, but if they are present, they are going to have some effect on the graph of the parent function. So we're going to go through them one by one, review what we've already stated, and I'm going to expand on one little idea about each of those 4 possible transformations. Okay, so let's talk about A first. Okay, A's job, it has 2 purposes when we're doing function transformations. Okay, A is going to vertically stretch or compress the graph. And what that means is if we were to grab the parent function on the top of the bottom like it was on a balloon or some piece of rubber that we could stretch, and we actually pulled it on the top and the bottom, that's the effect that it's going to have on the graph. So essentially it's going to become longer up and down, but because we're pulling it, it's actually going to maybe get a little skinnier as well. Okay, so if the value of a is greater than 1, so for example if a is 6 or 10, or even -3 or -5, because we're going to talk about the negative separately. So sign doesn't matter here. We're going to look at the value of the number. If the value of the number is greater than 1, we're going to say it's going to stretch the graph by a factor of whatever that value is. Okay. If we are talking about a number between 0 and 1, which another way of speaking about that is a fraction or a decimal, right? So if I talk about a number like a half or 0.25, or 1/10, things that are smaller than 1 but bigger than 0, right? Those are going to compress the graph. So again, think about taking something like a balloon and pushing it on the top and the bottom. It's going to get wider, okay, but narrower going up and down, right? So it has this effect on the graph of kind of distorting the way that it looks. Okay, if the a value is negative, the parent function is going to reflect over the x-axis. So that's a completely different purpose. We're going to look at the value of the number, and we're going to look at the sign of the number separately, and they do different things. Okay, here's the new thing. So that all that was review. We've discussed that before. Here's the new thing. A is always going to affect only the y part of any coordinate on the parent function. Okay, and it's going to affect that coordinate, that y value in the coordinate, using multiplication. Okay, so what that means is that if we were to make a list of all of the points on the parent function and the only thing we did was change a, none of the x parts of any of those points are going to change, only the y values will be affected at all. And you'll see this all come into play when we do an example problem. Okay, so let's keep going and just summarize and continue. So C is going to horizontally slide the parent function using by C units. Right, so the whole graph is not going to change shape. Okay, it's not going to do any reflecting. We're just going to take the entire thing and we're going to move it to the left and the right. Okay, and so similarly to A, C is only going to affect, and in this case C, the x part of the coordinate. So again, if we were to make a list of all of the values on the parent function, right, and then the only thing we did was we brought in a new C value, the only stuff that's going to change in any of those coordinates is the x part of that coordinate. And it's going to change those values using addition and subtraction. So again, you'll see that come into play. So I have in big blue letters down here, please be careful. Remember, C value, if I go to my my function itself, the function has a minus sign before C. So if I ask you for something like, for example, x minus 4, if I had that in this space here, x minus 4, and said, what is the value of C? The answer is the value is 4, and so that would be a positive value. It's going to move to the right. So even though I have an x minus 4 here, it's going to move in the positive direction. And if I had an x plus 4, I'd say my C value is negative 4, and that means it's going to move in the negative direction. Okay, so just be careful about that. When you're talking about C, you have to take into account that it's the opposite sign of what you're seeing because of the negative sign in our formula. Okay, so just very similar to D, or to C, D is going to do a slide as well, but it's going to be a vertical slide, so it's going to move it up and down. Okay, and here's the new part. D is only going to affect the y part of any coordinate on the parent function, and it also uses addition and subtraction. So notice both of my slides, vertical slide using D, horizontal slide using C, are addition and subtraction on the points. C works with the x part, D works with the y part, right? So they each have their own part of the coordinate, okay? So let's talk about B. B is the one that we've been avoiding, we haven't talked a lot about, because I'm telling you right now, B is a mess, okay? So here's what B does. B is going to do something similar to A, right? When we talked about A, we said grab it on the top and the bottom, and it's going to stretch it and compress it depending on the value. Okay? B does the same thing, but instead of grabbing it on the top and the bottom and pulling to stretch, we're grabbing it on the left and the right. So we're horizontally pulling it or pushing it, and it's going to have a similar effect that A does. It's going to distort the graph, make it look wider, but not as tall up and down, or something along those lines. Okay, here's where it gets a little bit challenging with B. We don't look at the value of B, we look at the reciprocal of B. So if, for example, just for this one, if I had something like 2x squared, and this was my function, so I'll call this f of x. Okay, if f of x is equal to 2x squared, I'd say my B value is 2. And I know this because 2 is being multiplied inside of the function. Before I square, I do the multiplying. But when I'm actually applying this function, I'm going to say the value that I care about is not 2. It is the reciprocal of 2, which is 1/2. So I would actually claim that if you have a value of 2 in here, I'm going to look at this, and because it's the reciprocal, and say that's going to be a compression by a factor of 1/2. So this is, even though the value is bigger than 1, it's actually we don't care about that, we care about the reciprocal. Okay, and again, just like A was a multiplication by the y value in the coordinate, B is going to be a multiplication by the x part of the coordinate, but it's a multiplication using the reciprocal. So A is just like you see it, okay? D is just like you see it. C is backwards, and B is backwards a little bit as well. So C is the opposite sign of what you see, B is the reciprocal of what you see. So those inside values are a little bit of a challenge that we're going to need to work with. Okay, so let's take a look at an example, and hopefully this will make a little bit more sense. Okay, so we can list the values. So we're just going to do, for example, problem number 3 and problem number 4 here. So if I were to take a look at these ones, I would say this is my letter A, and my letter B, and my letter C, and my letter D. So I would start by identifying each of those values. And it asked me to describe the transformations on f of x, right? So I had some function called f of x that had no a, b, c, and d's around it. And now I'm saying all of these new numbers are showing up and they're going to transform the graph. What happens? Okay, so in this case, I'm going to say, let's start off with A. Okay, so if I go back to what A said, okay, my A is going to be right here. Okay, A is going to stretch or compress depending on the value. And if A is negative, it's going to do a reflection. A is going to change the parent function using multiplication. So let's check that out. So I'm going to say the value of A is 3, and that's greater than 1. So I'm going to say this does a vertical stretch. Okay, and we describe it by a factor of 3. So that's telling people how much are we going to stretch it. We're going to multiply by 3. Okay, it's also going to do a reflection, okay, over the x-axis, and that's because the 3 is negative. Okay, so we have two different transformations happening just because of negative 3. Okay, I'm going to skip B because again that's the most challenging of them. Let's talk about C. So C, okay, so let's make bullet points here. C is 7 that I see, but remember we said in our head, actually it's the opposite of what you see, so it's actually negative 7. Negative 7 is a left, okay, slide, okay, or a slide left by 7, right? So we slide the whole graph to the left by 7. Similarly, D, okay, is going to move it up, and it's also a slide by 7 or by 1. Okay, so that's A is these first two. Okay, this does C. This is C, and this one's D. So let's talk about B. I saved that one to the end because again, it's the most challenging. So C, I'm going to actually say I'm not going to look at 4. The reciprocal is 1 over 4. Okay, and when I consider that value, that's a value between 0 and 1. So this is actually going to be a compress, okay, by a factor of 1/4. Okay, a horizontal compress. Let me be more specific. I'm going to put right in this little space here. A horizontal, okay, compress. Okay, so again, if this was negative, it would also do a reflection, but we're really focusing on what it's going to do. So there's lots of different changes happening in this one. So the last, let's do number 4 as well. This one we should be able to do pretty quickly. We'll do it a little bit with a little bit more speed. So I have an A value here. That's -1. I have a B value, a C value, and a D value, just like I had before. Okay, so because the 1 is 1, right? It's actually not going to change anything. It's not going to stretch or compress vertically. It's got to be bigger than 1 or smaller than 1. 1 is our neutral value. Okay, so I am still going to get that reflection. So I'm going to get a reflection, and again, I need to be specific because B is going to do a reflection as well. So this is reflection over x-axis. Okay, so that's one description. Okay, I'm going to do D again. So this is my A. Okay, D. That's pretty easy. That's a down, slide down by 3. Okay. Okay. And now, when I talk about the inside, we have an issue. If you compare problem number 3 and problem number 4, problem number 3 is in a factored form, right? I factored the 4 out, and if I ask you what value is in front of x, the answer is 1, right? The coefficient of x is 1. If I come over to this one, the coefficient of x is 2. That's bad. Right, if I go back to where we started, okay, if you notice, in my original form, the form where we're talking about A, B, C, and D, the value in front of x, the coefficient of x, is 1, and that has to be true before we can talk about B and C. So let's go back and try this again. We need to do one little fix here. In this case, I need to take this expression that says 2x plus 6, okay, and I'm going to turn it into 2 times x plus 3. Okay, and now I can say that there's a 1 in front of x, and I can describe my values. This is really important because if I had asked you what C was looking at this problem, it looks like the answer is 6. But when I come up to this new version where it's in factored form, the answer is it's actually only 3. So you have to be careful that it's in its factored form, and the coefficient of x is 1. Okay, so now let's talk about C. C is actually going to be a -3 value because I'm going to look at this one, not the unfactored form. So that's going to be a left by 3, not by 6. That's a spot where a lot of people make mistakes. B, again, I'm not going to look at the 2. I'm going to say this is really 1/2 in its factored, in its reciprocal form. So I'm going to say that this is a horizontal, okay, compression by a factor of 1/2. Okay, so again, there's lots of little things that are strange happening on the inside of the function we have to worry about. The reciprocal of B, the opposite sign of C, and now we're adding one more thing onto that. We're saying before you can even talk about C or B and C, we actually want to make sure that it is in a factored form, so the coefficient of x is 1.